what could it mean to say space-time is a quantum error-correct encode? And to address that question and the related question, right, in what sense does the Qecc interpretation entail that space-time is a quantum error-correct encode? We need to first understand the motivation for the quantum Qecc interpretation. And this involves a particular problem associated with the AdS CFT dictionary known as the bulk locality paradox. So that'll be the topic of part 2 of this lecture. And then in part 3, we'll review first the basic notion of a quantum error-correct encode, and then how interpreting AdS CFT in terms of a Qecc addresses this problem called the bulk locality paradox. And then in the 4th part of the lecture, I'll return to these general questions. What could it mean to say space-time is a quantum error-correct encode? Okay, so part 1. So let's recall sort of very basic features of this thing called the AdS CFT correspondence. So it's supposed to be a correspondence between a theory of gravity in d dimensions in AdS spacetime, anti-de Sitter spacetime, or in a spacetime that asymptotically approaches AdS spacetime on the one hand, and conformal field theory, CFT, in one less dimension on the other hand, right? And so typically we're asked to imagine the AdS theory of gravity as existent in some bulk spacetime, and the conformal field theory that's dual to it as existent on the boundary of this bulk spacetime. And speaking generally, right, there seems to be a redundant aspect to this correspondence in the sense that boundary degrees of freedom in d-1 dimensions are mapped to bulk degrees of freedom in 1 greater dimension. And this has suggested to some authors a quantum error-correct encode, which in broad outline is a way to protect information redundantly against environmental degradation, right? So if you have information encoded in a single qubit, you can protect it redundantly against environmental corruption by attaching some number of ancillary qubits to it, and then recoding your information in this larger n-qubit state in such a way that you can recover the initial information if some number of those ancillary qubits have been corrupted or erased for that matter. Right? So there seems to be a similarity in redundancy, right, between on the one hand AdS CFT and on the other hand a Qecc. And on the surface, this has led to this mysterious claim, right? So in a series of lectures, one of the authors of the Qecc interpretation has asked this question: is space-time a quantum error-correct encode? This is the title of some talks given by John Preskill. And this has been picked up in the popular literature, right? So a recent article in Quanta magazine has the title, How Space and Time Could Be a Quantum Error-Correct Encode. So what could this mean? So towards some initial demystification, so an anticipation of the story to come, so it turns out the Qecc interpretation of AdS CFT is intended as a response to this problem called the bulk locality paradox. Namely, under reasonable assumptions about locality, a standard way of representing a local bulk field on the boundary entails that it is trivial. Now, there's an analogous condition in the Qecc, namely local operators that detect and correct errors act like the identity on what's called the code space. And so in very broad outline, right, the Qecc one aspect of the Qecc interpretation of AdS CFT is the following. It is based on the claim that a certain collection of bulk states is dual to a subspace of boundary states that forms the code space for this thing called the code space for QECC. Right, so roughly, there's certain structural aspects associated with the QECC that seem to be mimicked by certain structural aspects associated with the AdS CFT correspondence. But to step back for a minute, what does this have to do with spacetime? So this question I'd like to return to eventually, right at the end and in the last part of the lecture. But between now and then, I'd like to get a bit firmer of a grasp on this initial motivation for the QECC interpretation, what's called the bulk locality paradox. So this is the subject of part 2 of the lecture. The topics here are going to be, we'll first briefly review what I take to be the standard presentation of the AdS CFT dictionary. And then it's going to be a limitation of this standard presentation that leads to a program in AdS CFT called bulk reconstruction. And then the bulk locality paradox is going to be a particular problem associated with the program of bulk reconstruction. Okay. So part 2 of the lecture, the bulk locality paradox. For the technical details associated with this part, and actually part 3 too, I'm relying very heavily on a review article by Daniel Harlow from 2018. This consists of his lectures on AdS CFT. And so Harlow and other authors identify what they call 2 different, distinct versions of the AdS CFT dictionary. Right, so the dictionary is supposed to be one way of representing this correspondence between this bulk theory of gravity on the one hand and the boundary CFT on the other. So in the differentiate version of the dictionary, we identify partition functions. Right? The partition function of the bulk theory on the left is identified with the partition function of the conformal field theory, the CFT, on the right. Right? In the path integral formulation of quantum field theory, it's these partition function objects that are the objects of interest. Right? They're the mathematical objects that you use to derive these other things called correlation functions. I guess in QFT, the partition functions are called generated functionals. So in the differentiate version of AdS CFT dictionary, the partition function of the bulk is given as a functional of a field variable identified as the boundary value of a bulk field, right? And that's identified with the partition function of the boundary CFT, in which the field variable is identified as a source term that couples to boundary operators. And again, right, the role that partition functions play in quantum field theory is you can derive correlation functions by taking appropriate functional derivatives of the partition function of your theory, the generated functional of your theory. So in particular, right, this differentiate version of the AdS CFT dictionary lets us derive boundary correlation functions as functional derivatives of the partition function of the bulk theory. And it's correlation functions that are the observables of interest in a quantum field theory. Right? They take the form of vacuum expectation values of products of the fields in your theory. And these are the things that you can then compare with data, things like scatter and cross sections. So one way of understanding kind of the significance of this differentiate version is to view, I take it, the AdS CFT correspondence as an approach to quantum gravity. Right? So the idea is we don't yet have a full mathematical grasp of a quantum theory of gravity as represented by some bulk theory of gravity. What we do have a good mathematical grasp on are things like conformal field theories. So the differentiate version allows us to take an object that we have a good mathematical grasp on, say a correlation function in a conformal field theory, and use it to probe the nature of this mysterious bulk theory of gravity on the right-hand side. So that's the differentiate version of the AdS CFT dictionary. And it goes back to a couple of articles in 1998 by Goopser and colleagues and by Ed Witten. Now, Harlow and other authors also identify what they call an extrapolate version of the AdS CFT dictionary. And it's in the extrapolate version, we identify on the left an appropriate limit of a bulk field with a local boundary operator on the right. Right, so intuitively, we take a bulk field and we extrapolate it to the boundary, and the result is a boundary operator. And again, the role of the extrapolate version ultimately is to be able to derive boundary correlation functions. But in this case, the way we do it is by extrapolating a bulk correlation function to the boundary, right, taking this appropriate limit of a bulk correlation function. Many authors view this extrapolate version of the AdS CFT dictionary as analogous to the LSC formula in quantum field theory. Right? So you use the LSC formula in quantum field theory to calculate correlation functions of a non-trivially interacting quantum field. In this case, that would be the object on the left, in terms of an appropriate limit of correlation functions of a non-interacting quantum field. Right? So again, the intuition is we're using objects that we have a firm mathematical grasp on, namely non-interacting quantum field theory, and we're using constructions from it to probe the mysterious nature of something we don't really have a firm grasp on, namely a non-trivially interacting quantum field theory. Right, so the analogy is in the QFT context, the non-interacting, the objects of interest in the non-interacting theory are these asymptotic, are local non-interacting fields and non-interacting particles at asymptotic times that then come to interact at finite times and then scatter into free fields and free particles at asymptotic times again. Right? So we're using something we have a good grasp on at asymptotic times to probe the nature of something we don't really have a good grasp on at finite times. And the analogy is with using boundary operators on the boundary to probe the mysterious nature of the bulk. So the extrapolate version of the AdS CFT dictionary goes back to an article, and again, another article in 1998, this one by Banks and colleagues. So two different versions of the AdS CFT dictionary, and it turns out they're equivalent. This was demonstrated by Harlow and Stanford in 2011, in the sense that the boundary correlation function you can calculate using the differentiate version is identical to the boundary correlation function you can calculate using the extrapolate version. Now, in the same breath, the authors who demonstrate this equivalence also raise concerns about both versions. Right? So I take it the concern is that in both versions, what we're identifying are bulk quantities near the boundary on the one hand, with boundary quantities on the other hand. Right. So in the differentiate version, the bulk partition function is a functional of a boundary value of a bulk field. And in the extrapolate version, what we're identifying with a boundary operator is an appropriate limit, right? As we approach the boundary of a bulk field. And so, for instance, Harlow asks the following questions. Well, what if we're interested in bulk fields located deep within the bulk, far from the boundary? What if we're interested in observables behind the event horizon of a bulk black hole? For these sorts of observables, Harlow says, right, the quote, we'd like to back off of the extrapolate dictionary, and equivalently, I guess, the differentiate dictionary. And backing off of this standard way of presenting the AdS CFT dictionaries leads to this program in AdS called bulk reconstruction, the goal of which is to be able to represent a bulk field located anywhere in the bulk in terms of a boundary construction. So as I understand it, the general idea involves the following 3 steps. So in the first step, you take your bulk field located at some arbitrary bulk point, X, and you quantize it, right? You express it in terms of creation annihilation operators that act on a Fock space. In the second step, you then use the extrapolate dictionary to express a boundary operator in terms of the creation annihilation operators of your bulk field. And then in the third step, you Fourier transform step 2 to get an expression of your bulk field explicitly in terms of this boundary operator. And the result takes this general form where on the left-hand side, we have our bulk field, and on the right-hand side, it's being represented not by a boundary operator by itself, but by the integral over some boundary region of a boundary operator smeared across this region by an appropriate smearing function. And there can be the first step can be done in at least 2 distinct ways, depending on the coordinates that you use. So if you choose global coordinates, a set of coordinates that completely covers your bulk space-time, then it turns out the boundary region that you integrate over in this representation is the set of boundary points that are space-like separated from your bulk point, little x. But you can also use coordinates, sort of the correlates of what are called Rindler coordinates in the Minkowski space-time context. And Rindler coordinates, or in this case, maybe AdS Rindler coordinates, completely span a wedge region of the bulk space-time, right? What's called the AdS Rindler wedge. And the resultant boundary representation is an integral over a boundary region that consists, in this case, of the intersection of the boundary with this thing called the AdS Rindler wedge. Now, as I understand it, the AdS Rindler wedge can be generalized, and what you get as a result is a bulk region with respect to a particular boundary subregion. And this generalization of the AdS Rindler wedge is called the causal wedge associated with a given boundary spatial subregion. So the context is take a spatial slice of the bulk space-time, and where it intersects the boundary, call that surface sigma. R is supposed to be a subregion of sigma, and it's represented by this blue surface on the diagram on the right. The causal wedge of R is then defined in the following way. It's a boundary region, namely it's the boundary region given by the intersection of the bulk causal future with the bulk causal past of the boundary domain of dependence of R. So the domain of dependence of a space-like surface, right, consists of all points such that any causal curve through that point intersects the space-like surface in exactly one point. So typically the domain of dependence of a surface like R is interpreted as the set of points that are causally determined by R. Right? And again, in this sense that any causal curve through a given point registers on R. So the boundary domain of dependence of this spatial subregion R is this causal diamond that's anchored at R. And the causal wedge then consists of all bulk points that are causally accessible from this causal diamond boundary region. Right? All bulk points that are causally accessible from the boundary region that is causally determined by R. So that is the causal wedge associated with a boundary spatial subregion R. And with respect to this bulk region, we can now define a particular way of representing a bulk field in terms of a boundary construction called the AdS Rindler representation of a bulk field. So take your bulk field, confine it to the causal wedge of some boundary spatial subregion R, and then it turns out you can represent that bulk field in terms of a boundary operator located at some boundary point capital X in R, smeared over, in this case, the boundary domain of dependence of R. So the AdS Rindler representation of a bulk field represents a bulk field at a point in the bulk as a boundary operator with support on a boundary spatial subregion. Now, associated with this AdS Rindler representation is the following conjecture. This is called the causal wedge reconstruction conjecture. This is the claim that for any boundary spatial subregion R, any bulk field in the causal wedge of R can be represented by a boundary operator on R in terms of this AdS Rindler representation. So this seems to be a powerful entry, right, in the AdS CFT dictionary. If you're interested in representing bulk fields deep in the bulk in terms of boundary, some sort of boundary construction, if you're interested in bulk observables, perhaps located behind the event horizon of a bulk black hole, then you might consider, right, this thing called the AdS Rindler representation. I think it's a way of extending the standard presentation of the AdS CFT dictionary to, in principle, cover these interesting cases of bulk observables. On the other hand, it's non-local, right? Under it, we are representing a bulk field located at a point in the bulk by a boundary operator with support on a boundary region. And moreover, without further ado, it turns out to be trivial. And this is the essence of the bulk locality paradox. So the bulk locality paradox is the following claim. The AdS Rindler representation of a bulk field phi, with respect to some boundary spatial subregion R, is trivial. And the argument for the claim was presented in two articles from 2015, one by Al-Meiri and colleagues, and the other by Postowski and colleagues. And it's also summarized in the review article by Harlow. So as I understand it, the argument is based on the following three premises. And the first is following for any bulk field at some bulk point little x and any boundary operator at some boundary point capital Y on the same time slice, there's an AdS Rindler representation such that the boundary operator lies in the complement of R. And so it commutes with the AdS Rinder representation. And this is entailed by local commutativity of the boundary CFT. So again, the idea is take our bulk field located at some bulk point X, identify the corresponding boundary spatial subregion for which X lies in the causal wedge. And you can always find a boundary point Y in the complement of R and a boundary operator located at Y, such that that boundary operator commutes with the AdS Rinder representation of the bulk field. Now, one implication of this is that a bulk field admits multiple AdS Rinder representations, each commuting with some arbitrary boundary operator on the same time slice. Right? So in the diagram at the bottom, we have the same bulk field located at the same bulk point X, but now we've identified it with a different, with the causal wedge of a different boundary spatial subregion, R prime. And with respect to R prime, we can find a boundary point, capital Y prime, and its complement, and the boundary operator located at Y prime that, again, has to commute with the AdS Rinder representation, this time in terms of R prime as opposed to R. So that's the first premise. The second premise then is an assumption of uniqueness, namely, for any given bulk field, all the various AdS Rinder representations of it are equivalent. Right? For any given bulk field, there's just one unique AdS Rinder representation of it. And we might motivate this uniqueness assumption perhaps by referring to this general idea of duality, right? AdS CFT is supposed to state a duality between bulk quantities on the one hand and boundary quantities on the other. Right? And so far as duality is a one-to-one relation, we'd like these correspondences to be one-to-one relations. Right? So in this context, we'd like our bulk field to correspond to one and only one AdS Rinder representation. So that's the assumption of uniqueness. And then the third premise is the following. If we assume the boundary conformal field theory satisfies what's called the time slice axiom, then we're led to the conclusion that the one unique AdS Rinder representation of any given bulk field must be a multiple of the identity. So the time slice axiom is sometimes called primitive causality. And here's one formulation of it. So let sigma be a Cauchy surface in a given space-time, and let U be an open neighborhood of sigma. Then the algebra of observables generated by local operators with support in U corresponds with the algebra of observables on the entire space-time. Or in other words, the algebra of observables corresponding to U acts irreducibly on the correspondent state space. So one way I've seen to motivate this time slice axiom, primitive causality, is that it turns out that it allows you to formulate the dynamical laws of your theory as hyperbolic differential equations. So if you want your equations of motion to take the form of hyperbolic differential equations that allow you to sort of deterministically evolve data from one Cauchy slice to another, then you might be motivated to adopt primitive causality. Now, from linear algebra, let's recall Schur's lemma. Any operator that commutes with all irreducible representations of an algebra is a multiple of the identity. So the conjunction of the time slice axiom and Schur's lemma entails, for this setup for a Cauchy surface and an open neighborhood of the Cauchy surface, any operator which commutes with all local operators with support in U must be a multiple of the identity. And it looks like that's the case with our AdS Rindler representation. Under reasonable assumptions about locality, namely, if we assume our boundary theory, our CFT satisfies local commutativity and the time slice axiom, and we're interested in representing bulk observables far from the boundary in terms of this thing called the AdS Rindler representation, then we're in trouble. Right? Unless that is, we can figure out a way of understanding how uniqueness might fail. And again, that, at least on the surface, it's a bit problematic because it looks like uniqueness is associated with the claim that, this way of representing a bulk field on the boundary is just another manifestation of the duality associated with AdS CFT. The Qecc interpretation of AdS CFT now is intended, at least initially it was intended, to address this issue. It's supposed to be a way of understanding how uniqueness can fail for the AdS Rindler representation and still be able to, in some sense, interpret AdS CFT as encoding a duality relation. Okay, so that's the bulk locality paradox. So now I'd like to move on to the third part of the lecture. What exactly is a quantum error correct encode? What is the Qecc interpretation of AdS CFT, and how does this interpretation in particular address what we just reviewed, this bulk locality paradox? So the Qecc interpretation of AdS CFT was presented by Ha'iri and colleagues in an article in 2015. And again, it's reviewed by Harlow in his 2018 review article. So again, right, in general, it's supposed to be a correspondence between structural features of a Qecc and structural features of, in particular, the AdS Rindler representation of a bulk field on the boundary, that aspect of AdS CFT. So the first order of business is to understand this concept of a quantum error correct encode. And in particular, the context here is an erasure protection quantum error correction code. So this thing consists of two parts, right? The first aspect of an erasure protection Qecc is an Encoded Hilbert space, what's called a physical Hilbert space. So a qubit is sort of a generalization of a qubit. A qubit you can think of as a state of a two-state quantum system. A qubit is a state of a d-state quantum system, for d is some arbitrary integer. So we first want to identify an Encoded Hilbert space that we call the physical Hilbert space, decomposable into two factor spaces, hm sub r, hn minus m sub r bar, where hm sub r consists of m qubit states with support in some set r, and n minus m sub r bar consists of n minus m qubit states with support in the complement of r. In addition to this physical Hilbert space, we also want to identify an encoded map that encodes some number k of what are called logical qubits and some number n greater than k of what are called encoded logical qubits of a subspace of our physical Hilbert space, in such a way that the initial logical qubits can be recovered if access is limited to some set R of m less than n of our physical encoded logical qubits. Right? So again, the idea is we have information encoded in some number of, in general, qubits. To protect it against erasure, in this case, we attach some some other number of ancillary qubits to form an encoded state, right? And then we encode the original information in this encoded state in such a way that we can recover the initial logical qubits if some number of our encoded logical physical qubits have been erased. A redundant way of encoding information. Now, Harlow demonstrates the following claim. So this is a necessary and sufficient condition for the existence of an erasure protection encoded map. So the claim is an encoded map exists if and only if our set R of, so R would be the set of accessible qubits, physical qubits, can be decomposed into the union of two subsets, R1 and R2, with K and M minus K qubits respectively. Right? K is the number of our original logical qubits, such that the basis states of the code space can be expressed by this relation, which involves a unitary operator, U sub R, acting on not just a basis state of our original logical qubits, that's the I state, but the I state, basis state supplemented by some number of ancillary qubits, right, in a particular state chi. So take a basis state of our original logical qubits, attach an ancillary number of qubits to it, then act on what we get as a result. So the result is an encoded state, right? Act on that encoded state with this unitary operator to transform the encoded state into a basis state of our code space. And it's this unitary operator that encodes, that represents the encoded map. And this expression can be represented by what's called a quantum circuit diagram on the right here, right? So in the lower left-hand corner, we have our K logical qubits in some initial state psi. We attach to them some number of ancillary qubits, in fact, n minus K of them, right, in some state, specific state chi. We act on the result with our encoded map U. And that's supposed to represent this way of redundantly encoding our original information in this larger set of qubits that protects it against erasure. So maybe to make this a bit more concrete, let's look at a particular example of an erasure protection encoded map. This is an example described in more detail by Harlow. So this is called the 3 Qecc code. Right, a Qecc is a state of a 3-state quantum system. And in the 3 Qecc code, we encode, we take one logical Qecc and encode it in 3 physical Qeccs in such a way that we can recover the logical Qecc if we only have access to 2 of the 3 physical Qeccs that we've encoded it in. And the encoded map takes the following explicit form. Right, so the encoded map is this unitary operator represented by this table down here. So it's a 2 Qecc operator. It acts on 2 Qeccs in the following way. Right? It takes 0, 0 to 0, 0, 0, 1 to 1, 1, etc. Right, so to get a basis state of our code space, we take a basis state of our original logical Qecc, attach 2 Qeccs in this particular state chi, namely the state 0, 0 plus 1, 1 plus 2, 2, and then act on this 3 Qecc system that results with our unitary, in this case, acting on Qeccs 1 and 2. And that'll give us a basis state in our code space. So if we, for instance, if we take the 0 basis state of our logical Qecc, attach this 2 Qecc chi state to it, we get 0, 0, 0 plus 0, 1, 1 plus 0, 2, 2. Now act with our unitary on the resultant 3 Qecc state, And what we get is 0 tilde, the 0 tilde basis state of our code space. And similarly for the other 2 basis states. So in this way, we've encoded our single logical Qcert in a 3 Qcert system, a 3 Qcert state. Right? And the claim is we can now recover the single logical Qcert if we only have access to 2 of these 3 physical Qcerts. And the recovery protocol consists of the following. So it does assume that we know which physical Qcert gets erased, right? So if we know that physical Qcert 3 has been corrupted, has been erased, then we recover our logical Qcert by acting on our encoded logical Qcert with the adjoint of U, in this case, acting on Qcerts 1 and 2. And if you work through the linear algebra, that reproduces the original logical Qcert in the first Qcert position. And similarly, if we know Qcert 2 has been erased, then the protocol is act on our encoded logical Qcert using the adjoint of U, now acting on 3 and 1. And we get the logical Qcert in the third Qcert position. So does that make sense? So again, it's conceptually, again, this is a way of encoding information redundantly against the threat of erasure. So that's an erasure protection quantum error correcting code. So the next question then is, right, what does this have to do with AdS CFT? Towards making the link with AdS CFT, let's now review 3 additional necessary and sufficient conditions for the existence of a erasure protection encoding map. And it turns out all 3 of these additional conditions are equivalent to each other. So for the proofs of the equivalence of these conditions, I'll just refer to the original article or the review article by Harlow. So it turns out the one equivalent necessary and sufficient condition for the existence of an encoded map is what I'll call the Qecc condition. And this is the requirement that any n-m-qubit operator that acts on the complement of R acts like a multiple of the identity on the code space, in the sense that if you project it into the code space, it's a multiple of the identity. And this is suggestive of the bulk locality paradox, right? The claim that the AdS render representation of a bulk field is trivial. Now, an equivalent necessary and sufficient condition for an encoded map is what I've called the erasure protection condition. And this is the requirement that any n-qubit operator on the code space can be expressed as an m-qubit operator, right? M is less than n, with support on R, in the sense that they both act in the same way on elements of the code space. And this is reminiscent of the causal wedge reconstruction conjecture, right? The claim that a bulk operator with some number of degrees of freedom located in the causal wedge of a spatial subregion can be represented by a boundary operator with less degrees of freedom with support on that on the boundary spatial subregion. And then there's a third necessary and sufficient condition for the existence of an encoded map. This is the requirement that within the code space, any n-qubit operator commutes with all n-m-qubit operators with support on the complement of R, in the sense that if you project their commutator into the code space, it's 0. And again, there seems to be a feature of the bulk locality paradox that's similar to this, right? The AdS render representation appears to commute with all boundary operators that are all on the same time slice. Now, to make these similarities more concrete, so at this point, right, these are just sort of similarities between certain aspects of Qecc on the one hand, and certain aspects in particular of the AdS Rinder representation on the other hand. So to make these similarities maybe a bit more concrete, I'd like to briefly review yet another equivalent necessary and sufficient condition for an encoded map. And this takes the form of a claim that was proven by Harlow in another article from 2017. So this is not his review article. So in this article, he proves the following claim. Let H be a finite dimensional Hilbert space, which decomposes into two vector spaces, HR and HR bar. Let HC be a subspace of H, and let M be a von Neumann algebra on the subspace. Then Harlow demonstrates that the following two conditions are equivalent. The first is just this erasure protection condition B from the previous slide. And the second condition is what Harlow calls the finite dimensional RT formula. And in the context of this claim, this is the following statement. There is an operator L sub R in M such that for any state rho tilde on M, this following relation holds. So the object on the left is the von Neumann entropy of the reduced density operator rho tilde sub R. This is sometimes called the entanglement entropy associated with the reduced density operator rho tilde sub R. And the quantity on the right consists of two terms. The first term is the trace of the product of rho tilde with this operator L sub R, right? That's just the expectation value of the operator with respect to the state rho tilde. And then the second term is the von Neumann entropy of the state rho tilde. So at this point, this is just a relation between quantities associated with a Qecc. So to link Harlow's claim explicitly with constructions in AdS CFT requires a brief review of two such constructions. And the first is this thing called the RT formula in the AdS CFT context. Right. So I guess in my second lecture today, I'd like to discuss this formula in a bit more detail. It was given by an article in 2006 by Ryu and Takayanagi. And it refers to the following constructions in AdS CFT. So again, we have a boundary spatial region, a surface that's divided into some subregion R and its complement. R in this case is represented by this blue surface. Now corresponding to R, we define a particular surface in the bulk called gamma sub R. It's defined to have the same boundary as R, and it's defined to be that bulk surface that has the same boundary as R with the minimal area. Right. So there could be all kinds of bulk surfaces that have the same boundary as R. Gamma sub R is defined to be that bulk surface that has the same boundary that also has the minimal area. That's gamma sub R. And with respect to R and gamma sub R, you can also define another bulk surface, call it H sub R, which is bounded by the union of R and gamma sub R. So with respect to these constructions, the RT formula is the following statement. On the left is the entanglement entropy of a boundary subsystem localized in R. So think of a boundary composite system localized on this boundary, complete boundary spatial surface. It's decomposed into two subsystems, one of them localized in R and the other one localized in R bar. And suppose the boundary, the physical system is in an entangled state, then the entanglement entropy of the subsystem, the degrees of freedom localized in R, is given by the expression on the left. And on the right, we have the area of the minimal area bulk surface corresponding to R divided by 4 times the Newtonian gravitational constant, plus the second term, which is the entanglement entropy of a bulk subsystem localized in H sub R. Right. So this is a statement in AdS CFT, right? So roughly you might think of it as an additional entry in the AdS CFT dictionary. It relates a quantity, a boundary quantity on the left with, in this case, certain boundary bulk quantities on the right. So that's one link between Harlow's formula and AdS CFT, Harlow's claim on the previous slide in AdS CFT. And to further establish the link requires another AdS CFT construction. This is called the entanglement wedge of a boundary spatial subregion R. And this is defined to be, it's a bulk region defined as the bulk domain of dependence of this H sub R bulk surface. Sometimes H sub R is called, I guess, the homology surface that corresponds to R and gamma R. And this notion of an entanglement wedge, I take it, was introduced by Hedrick and colleagues in an article from 2014. So it should be compared with what we earlier discussed, this thing called the causal wedge of R. Right? So the causal wedge of R is also a boundary subregion associated with, I'm sorry, a bulk region associated with a boundary subregion R. But it's obviously the definition is different. It turns out the entanglement wedge and the causal wedge coincide for simple examples of boundary spatial subregions. Where they can differ is when the boundary spatial subregion R consists of the union of 2 disjoint subregions. Right. So in the diagram at the bottom, R is the union of 2 disjoint boundary subregions, R1 and R2. We can still define a corresponding minimal area bulk surface, gamma R, right, as the bulk surface with the same boundary as R with a minimal area. But in this case, it's now going to, again, also consist of the union of 2 disjoint surfaces, gamma 1 and gamma 2. H sub R, right, by definition, is the bulk surface bounded by R and gamma R. So it's going to consist of the union of the 2 red regions and the green region. And then it turns out, right, the entanglement wedge associated with this R is going to contain the red and green regions, whereas the causal wedge of the same boundary subregion R only consists of the red regions. So in cases like this, the entanglement wedge extends the causal wedge further into the bulk. Okay, so we can now make a more explicit connection between Harlow's claim on the one hand and features of AdS CFT on the other. So in Harlow's claim, we can identify the Hilbert space with the Hilbert space of our boundary CFT. The 2-factor Hilbert spaces can be identified with CFT degrees of freedom localized on the spatial region, subregions R and R bar. We identify Harlow's operator L sub R with the area operator applied to the minimal area bulk surface corresponding to R divided by 4G. We have to identify M with the algebra of bulk observables in the entanglement wedge of R. And then the subspace, Harlow subspace, is then identified as the subspace of CFT states that represent bulk states in the entanglement wedge of R under the AdS Rindler representation. So with this explicit map, we can then, well, the idea now is we can then extend this particular link that links Harlow's claim with AdS CFT to the other conditions that are equivalent, right, to the erasure protection condition for the existence of an erasure protection encoded map. And in that way, we obtain this Qecc interpretation of AdS CFT. So one way to represent it is in terms of this table, right? In the left column are structural aspects of a Qecc. In the right column are structural aspects of AdS CFT, right? And the Qecc interpretation is just a map between these structural aspects. So in the left column, we have a physical Qubit Hilbert space that corresponds in AdS CFT to a Hilbert space of our CFT decomposed in a particular way, right, with respect to some boundary spatial subregion and its complement. On the left, we have the code space of a Qecc that corresponds on the right to a subspace of CFT states that represent bulk states in the entanglement wedge of our boundary spatial subregion. On the left is we have the erasure protection condition that corresponds to this, right, this extension of the causal wedge reconstruction conjecture now to the entanglement wedge. Any bulk field in the entanglement wedge of a given spatial boundary subregion R can be represented as a CFT operator on R. On the left, we have the Qecc condition that corresponds in AdS CFT, right, to the statement any local CFT operator on the complement of R acts as a multiple with identity on bulk states in the entanglement wedge of R. And then finally, there's this correspondence between what Harlow calls the finite dimensional RT formula and the full-blown RT formula in AdS CFT. All right. Again, there's this redundancy aspect associated with the Qecc, and that seems to be reflected in the AdS CFT context in the following way. Namely, the information associated with a CFT operator with support on a boundary spatial subregion R is protected against the erasure of degrees of freedom in the complement of R by encoding it redundantly, i.e. non-uniquely, in an AdS Rindler representation of a bulk field in the entanglement wedge of R. Now, one way this redundancy associated with AdS CFT has been one way to view it. In fact, the way that Postowski and colleagues view it is in terms of viewing the code space as the space of low energy CFT states. Right? So the idea is that distinct CFT operators that act in the code space, in this space of low energy states, act in the same way when restricted, when confined to low energy states, but can differ on their actions, in their actions on high energy states outside of this code space, the subspace interpreted as a space of low energy states. All right, so that's the Qecc interpretation of AdS CFT. Right? Again, structural features of a Qecc and erasure protection Qecc are mapped onto structural features of AdS CFT. Now, I'd like to return to this question involving this general claim about space-time as being a Qecc, right? In what sense does this Qecc interpretation entail, if at all, the claim that space-time is a Qecc? And moreover, what could it mean to claim space-time is a Qecc? Again, right, under the Qecc interpretation, the bulk theory is a way of protecting boundary degrees of freedom against erasure. Right? And so we could ask, what does this have to do with space-time? A QECC is not the sort of thing associated with a space-time. Right? It's a physical Hilbert space and a particular way of encoding an encoded map. On the other hand, we might say a QECC can be realized by physical systems, and those physical systems can then be said to possess spatiotemporal properties. Now, one suggestion might be the following. To the extent that the bulk emerges from the boundary, and the boundary might be said to have the structure of a QECC or aspects of the structure of a QECC, then we might claim that the bulk spacetime emerges from a QECC, or at least from some physical system that realizes the structure of a QECC. But at least initially, there's one problem with the suggestion, and this has been pointed out by a number of philosophers of physics. Right? This bulk boundary duality is typically taken to be symmetrical, right? In the sense that it's exact. It's a one-to-one correspondence. And usually emergence is thought of as
John.
Sorry,
there's a question from the audience.
Uh-huh.
Okay. May I ask something? Can you hear me?
Yes.
When you say emerge, it is in the sense that what happened in the bulk is not completely determined by what happened on the boundary. And if yes, how it is possible to conciliate it with the fact that in the bulk we have only redundancy, not more information? Thank you.
Yeah. So I take it that the concern is just that there's this on the surface there's supposed to be a duality relation between the bulk and the boundary, and the concern here is how to understand emergence. I guess the concern is how to understand emergence in terms of a duality relation, right? Where emergence is supposed to be this asymmetric relation that sort of flows in one direction, right? We want to say emergence relates a base system with an emergent system in such a way that the emergent system can be said to emerge from the base and not vice versa, right? We don't want to say the base system emerges from the emergent. And so without further ado, that complicates any emergentist interpretation of not just AdS CFT, but I take it any sort of duality relation in general. Right, and on top of that, you might add this further concern about how to understand this redundancy between bulk and boundary in terms of a duality relation, as well as an emergence relation too.
Okay. Thank you very much.
Thank you.
You need to come here if you want to be here. It's a bit.
Yes, okay. I understood. Thank you very much.
Thank you. Yeah, right. So a number of philosophers of physics, included Qecc and Dennis Deeks and Sebastian, and a number of his articles with colleagues have raised this concern about any attempt to interpret AdS CFT in terms of the bulk emerging from the boundary. So one way to address this concern is to attempt to come up with a way of underwriting the asymmetry that assumedly is needed to underwrite a notion of emergence. So here's one proposal for this, for attempting to support a notion of emergence in the face of duality in this particular context of the QECC interpretation. So the idea is going to be, we'd like to realize an erasure protection QECC in the first instance as a physical system, in particular as a discrete lattice system of qubits. And this actually takes the form of what's called the happy code in the physics literature. So the idea is going to be to take this thing called the happy code and view it as representing a physical system. Right? And then the next step is to formulate an appropriate continuum limit of this discrete physical system that ideally should reproduce at least those aspects of AdS CFT that correspond under the QECC interpretation to structural aspects of a QECC. Right? And then we can then use this continuum limit then as the basis for an emergence relation, an emergentist interpretation of AdS CFT. And in particular, we might interpret it in terms of the emergence of, for instance, bulk spacetime. And in that way, we might be able to support this claim that spacetime isn't literally a QECC, but perhaps emerges in some appropriate limit from a physical system that realizes the structure, or at least aspects of the structure of the QECC. So that's the story in brief of what I'd now like to present in the remainder of the lecture. And this is going to lead to what I suggest we call the happy code interpretation of AdS CFT. And the last part of the lecture, I'd like to compare that particular interpretation, think of it as kind of a modification of the QECC interpretation with various options, various proposals in the philosophy of physics literature on how to interpret dualities in general. So the first step is to realize this QECC structure as a concrete lattice system of qubits. Let's call this the happy code realization of an erasure protection QECC. And this was introduced in an article. It's the same article that I've referred to on a couple of previous slides by Postowski and colleagues. In this case, the colleagues are Yoshida, Harlow, and Preskill, right? And their last names form this acronym HAPPY. So that's the happy and happy code. So it's based on yet another way of representing an erasure protection QECC, in this case, in terms of what they refer to as a perfect tensor. So under this representation, an erasure protection QECC takes the form of a 2L index linear map from 1 qubit to 2L minus 1 qubits that protects against the erasure of any L minus 1 of the latter, the 2L minus 1 qubits. So the idea is as follows. So for example, the 3 qubit code that we looked at earlier, in this way of representing it, has L equal to 2, right? It encodes 1 qubit for one qubit in 3 qubits, right? 4 minus 1 is 3 against the erasure of any one of the latter of the 3. And we saw that a necessary and sufficient condition for it is that you can express it explicitly in terms of this relation between basis states of the code space and basis states of the logical qubit, right? In terms of a unitary map U and some auxiliary qubits in a particular state chi, right? So the idea simply is just to represent our unitary operator in terms of components of a tensor. Namely, this thing that Postowski and colleagues refer to as a perfect tensor, namely an even index tensor, such that any bipartition of its indices defines a unitary transformation. Right? In this case, we're partitioning the indices into the first three and a fourth one. So again, it's just a way of encoding the unitary encoded map, right? So that's the 3-qubit code expressed in the form of a perfect tensor. Another example is another erasure protection encoded map called the 5-qubit code. In this case, L equals 3, and the 5-qubit code encodes 1 qubit in 5 qubits against the erasure of any 2 of the latter. So it can be represented by the components of a 6-index perfect tensor, a perfect tensor with 6 indices. And again, right, these components simply encode the relevant unitary operator that represents the encoded map here. So that's another way of representing an erasure protection encoded map, right, in terms of the components of a tensor. And then the happy code takes the following form. So this is a diagram taken from the happy article. So it takes the explicit form of a 5-4 tiling of the hyperbolic plane. 5-4 refers to what each lattice face is a pentagon, that's 5, and 4 pentagons meet at a given vertex. So that's the 4 of the 5-4 tiling. And on this 5-4 tiling, we then place 1 6-index perfect tensor on each lattice face in such a way that one of its 6 indices remains free, uncontracted, and the other 5 are contracted with the tensors on adjacent faces. Right, so the red dots in this diagram represent the uncontracted indices of the 6-index tensors on each face, and the black lines represent contracted indices. So if you work your way out, we have this discrete system of perfect tensors, a network, a tensor network, right? This collection of tensors contracted with each other, such that all the interior tensors have exactly 1 uncontracted free index, and then the tensors on the boundary have some number of uncontracted indices too, represented by the white circles. So Pastowski and colleagues then prove 2 claims associated with this tensor network. And the first is that it forms a network that's equivalent to a single perfect tensor that encodes some number k of bulk logical qubits represented by the free indices, the red free indices, in some number in greater than k boundary physical qubits, right, represented by the white circles on the boundary, against the erasure of some number of the latter. Right? Given that, right, an erasure protection QECC can be represented in the form of the components of a perfect tensor. So that's the first claim. And then the second claim involves identifying lattice versions of the entanglement wedge of R and their RT formula in the AdS CFT context. So the claim is that lattice versions of the entanglement wedge and the RT formula can be constructed in the happy code. So this involves the following. So we first identify some subset of uncontracted boundary indices and call that subset R. So here's R on the boundary, the subset of the white circles, and then identify a minimum length cut that has the same boundary as the set R, and that divides the entire network into two perfect tensors, PQ, with P defined by the tensors in the region contained in R, that would be the red region, and Q by those in the region contained in the complement of R, so that would be the blue region. And then it turns out the lattice entanglement wedge, the lattice version of the entanglement wedge, call it epsilon of R, consists of the set of tensors that define P, the tensors in the red region, and the lattice RT formula is the statement that the entanglement entropy associated with the degrees of freedom in R is given by the length of this minimum length cut, where the length of the cut is equal to the number of indices that it cuts. Right. So again, the claim is there are these correlates of these two constructions in AdS CFT. So this suggests that we can include this additional column in our table of correspondences between Qecc and AdS CFT. Right. So now there are correspondences between Qecc and this particular realization of it, the happy code. And then we can also relate the structural features of the happy code with the relevant structural features of AdS CFT. All right. So that's amounts to the happy code realization, right, of a Qecc, erasure protection Qecc. Now, again, according to the proposal, we can imagine the happy code as realized by physical systems, right? Maybe spin systems that realize the qubits associated with the free indices of all these tensors. So think of the happy code as some discrete physical system on a lattice. Now imagine taking a continuum limit of this physical system, some appropriate limit, right? Maybe the limit as the number of vertices goes to infinity while keeping the ratio of the number of vertices to the area of a phase constant. And assumedly, we would expect to recover at least those aspects of AdS CFT, right, that are structurally similar to the Qecc structural aspects of the happy code. And this suggests that, right, now we can perhaps claim that CFT, both the boundary CFT and the bulk AdS theory of gravity emerge in this appropriate limit of this particular physical realization of a Qecc, this happy code discrete lattice system realization of a Qecc. Right, so the cartoon version of this is, right, at the fundamental level, we have this Qecc structure, right, involving physical qubits and encoded logical qubits. It can be realized by a physical version of the happy code, right, in terms of physical boundary qubits and bulk qubits. And then we obtain the AdS CFT correspondence as an appropriate continuum limit of the discrete system. And in this continuum limit, we might then we might then claim that the continuum limit underwrites an emergence relation to the effect that we can now say space-time emerges from this discrete happy code system. All right, so let's call I'll call this the happy code interpretation of AdS CFT. Right, it's an emergentist interpretation of AdS CFT based on the Qecc interpretation. So in the last part of the lecture, I'd now like to compare this happy code interpretation with a number of realist interpretive options that have been suggested in the philosophy of physics literature. In particular, an article by Baptiste Lebihan and James Reed from 2018 lists a number of alternate ways, options of realistically interpreting dual theories. So where does this happy code interpretation fall in these options? So one option Lebihan and Reed consider is what they call discrimination. So this is the view that only one of two dual theories describes an actual world candidate. Right, when it comes to AdS CFT, just one of these two theories should be interpreted as a potential representation of the actual world, not both of them. And this seems appropriate for the Qecc interpretation of AdS CFT, right? Under the Qecc interpretation, it's really the boundary CFT that's sort of the primary focus, right? And the bulk is considered, a way of redundantly encoding boundary degrees of freedom against the threat of erasure, right? So the bulk is just this instrument that we use to encode boundary degrees of freedom. And that suggests this view discrimination. But it doesn't seem appropriate. Discrimination doesn't seem appropriate for the emergentist happy code interpretation, right? Because under the happy code interpretation, both bulk and boundary theories arguably, or at least might be thought of as actual world candidates, as representations of actual world candidates, right? They both emerge from a more fundamental object that itself manifests the structure of a Qecc. Now, another realist option that Lebihan and Reed discuss is what they call common core. And this is the view that dual theories share a common mathematical core, right? So a number of philosophers of physics have I think, articulated a view that's sympathetic to common core. Tiziana Vistorini suggests this in an article from 2017, and Sebastian and Jeremy Butterfield have also suggested it in a number of their articles. Right. So, right, according to Sebastian and Jeremy, the common core can be thought of as a triplet involving states, quantities, and dynamics, and it's this triplet that both dual theories share in common. Right? And this seems eminently reasonable, right? Given the differentiate version of the AdS CFT dictionary, right? If we've identified the generated functionals of our two dual theories, then the generated functionals, the partition functions, are defined in terms of, right, the dynamics of the theory. And if they're identical, then assumedly we get maps between the states and the quantities of interest of our theories too. But Harlow has suggested various limitations of the differentiate dictionary, right? And he's wondered if we should back off from it. What if we want to represent objects, bulk quantities deep in the bulk in terms of boundary quantities, right? That motivates this bulk reconstruction program. And it's this problem with the bulk reconstruction program that ultimately motivates this Qecc interpretation. And with respect to the Qecc interpretation, right, one potential concern with at least this way of expressing a common core is the concern that a Qecc really isn't associated with the dynamics, right? So if we want to associate, say, the structure of a Qecc as perhaps a common core, then we might want to back off of including a dynamics in this common core. Maybe we should be satisfied with identifying perhaps a purely kinematical common core. Now, another realist option that Lebihan and Reed discuss is what they call overarching theory. And in this view, dual theories don't share a common core. Rather, they can both be embedded in some overarching theory or some underlying theory. Right, and the images of their embeddeds don't necessarily overlap. So one concern with interpreting with viewing the QECC interpretation as subscribing to overarching theory is perhaps this trivial concern: can we consider a QECC as a theory, right? A theory in which aspects of two dual theories can be embedded? It's not. If you identify a theory with a dynamics, then it's a bit of a question as to whether a QECC can be thought of as a theory. And moreover, in the emergentist happy code interpretation, we have this emergence relation, and the concern then is, can we think of the emergence relation as an embedding relation? So I think the happy code interpretation represents a different view that's distinct from these three options. And to make that a bit more explicit, so here are my cartoon versions of the last two options. Right, here's the common core view when applied to AdS CFT. Right, under the common core view, the CFT and the AdS theory of gravity share this common mathematical core. In the overarching theory view for structure, right, if you want to include things like a QECC as an overarching theory, the CFT and the AdS theory of gravity can be embedded in this overarching or underlying structure. And it seems to me that the happy code way of viewing AdS CFT is distinct from either of these two views. Right? Under the happy code interpretation, you might view the overarching structure as relevant aspects of a QECC, but the claim is not that the CFT and the AdS theory of gravity are embedded or embeddable in it. Rather, the CFT and the AdS theory of gravity emerge from it, perhaps represented by these dashed lines as opposed to the solid lines. And moreover, they emerge as different aspects of a realization of it. Okay, so arguably the happy code interpretation is a way of viewing the duality between AdS and CFT in a distinct way, other than some of these options that have appeared in the literature. So by way of concluding, is spacetime a QECC? What are we to make of this general claim? Right, the answer is no. On the surface, it doesn't seem to make much sense. One way to make sense of it is the following. Does spacetime emerge in a continuum limit from a discrete physical system on a lattice whose kinematically possible states realize a QECC? And the suggestion, my suggestion is possibly, right? That's the proposal represented by this happy code interpretation of AdS CFT.